There's a certain temperature, okay, above which you cannot liquefy a gas, and that's called the critical temperature. So below a critical temperature, you can actually liquefy or change the gas to either a solid or a liquid by simply increasing the pressure. You can maintain its temperature, but you can turn it into a solid or a liquid by increasing its pressure. Okay, and that's illustrated here. This curve right here, pressure volume, okay, curve here illustrates uh, gas that's liquefying as you change the pressure. Let's imagine. Let's try to understand what these curves look like. This is what the plot that you would get if for at a constant t. Okay, so these are what you call PV isotherms. These graphs right here. So it's a plot of pressure versus volume at constant temperature. So what does this ideal curve say? Pressure is inversely proportional to volume, right? That's Boyle's law. Imagine you have a gas with high volume right here, okay? Low pressure. What happens if you shrink your volume? Remember Boyle's law? Pressure goes down as volume goes up, pressure goes up as volume goes down at the same temperature, right? So if I were to shrink my volume, what happens to my blue curve right here? It starts to rise, right? Volume goes down, pressure goes up. As I keep going, as I keep compressing my gas, okay, my volume keeps going down, my pressure keeps going up. Okay, and that's the ideal behavior. Okay, now what does it mean when the real behavior is shown by this red curve right here? At this particular, let's say at this particular pressure right here, okay? At these 2 points right here, point A and point B. Point A is the ideal case, point B is the real case. What does that mean? The volume, the real volume is less than the ideal volume, right? V sub B is your real volume, and V sub A is the ideal volume. So what does this mean? That your gas is in such a case where attractive forces are important. So it's occupying a volume that's smaller than the ideal volume. But eventually what happens to that real gas? Okay, below a certain temperature, which we call the critical temperature, okay, eventually what happens to that gas? Okay, so again, it's the pressure still goes up, okay, as you lower the volume, okay, the pressure keeps going up. Eventually you reach a point though, okay, where, so let's imagine you have a gas right here, okay, you're trying to change the volume, you're lowering the volume of the gas, you're pushing it down, right? So as what happens as you push it down? The pressure goes up, okay? So right here, your pressure will be going up as you're changing the volume. As you're lowering the volume, the pressure will go up. But eventually you get to a point where, okay, you can change the volume, but the pressure is not going to change at that temperature. How could that happen? That's the point where your gas starts turning into a liquid or a solid. So if you squeeze it some more, okay, the pressure is maintained because the gas molecules leave the gas and go into a solid or a liquid. So you're maintaining that pressure. So this flat line right here, okay, the pressure at this point is called the vapor pressure of your solid or your liquid, depending on whether it's turned into a solid or liquid. So this flat line right here is the vapor pressure of the gas of the substance at that temperature, at the given temperature. Remember, these curves represent what we call isotherms. So at this particular temperature we're looking at, that would be the pressure of the substance. Okay, it's called the vapor pressure. So eventually, what happens if you keep squeezing it? What happens? Everything turns into a liquid or a solid. Okay, and it becomes very, very hard to squeeze that solid or liquid. So you're going to have to apply a very large amount of additional pressure just to cause a small change in the volume of that solid or liquid. Okay, so on this diagram then you would say that a point on this curve right here would represent a solid or a liquid. A point on this curve would be a gas. Okay, this would be a solid or liquid. A point here would represent what? A condition where you have a liquid and a gas, or a solid and a gas in equilibrium. So at the same time, okay? So if this is the overall molar volume, this is the overall volume, this point right here would be the molar volume of the solid or liquid, and this point right here would represent the molar volume of the gas. So that's a typical behavior of a gas that, if you squeeze at a given temperature, will turn into a liquid or solid. Okay? So let's look at this isotherm right here. Which of the labeled points, K, L, M, or N, would represent a condition where the substance is gaseous and deviates least from ideal behavior? This is pressure versus volume. Let's change this since your clickers have A, B, C, D, and E. Let's make this A, B, C, D, and E. Okay? So which labeled point on this diagram, this is an isotherm here, represents a condition where the substance would be gaseous and deviates least from ideal behavior? A, B, C, D, or E? Okay. Ideal gas behavior happens when? When did we say ideal gas behavior occurs? Low pressure. Okay, on this diagram, where is the low pressure? You want to try it again? Let's see. Okay, very good. Low pressure. Okay. So at point E, we said that, okay, this would be way over here. It's going to be ideal, right? So as you increase as you shrink the volume of the gas, at constant temperature, the pressure is going to be going up, right? Which labeled point on this diagram represents a condition where you would have a solid or a liquid? The whole thing is either a solid or a liquid. A, B, C, D, or E. Very good. Point A. All right. Why point A? Remember we said that as you shrink the volume, okay, the pressure is going to go up. Eventually, it reaches a point where the pressure levels off even if you keep shrinking it, even if you keep squeezing it. And the reason for that is the gas molecules go into a solid or liquid as you keep squeezing it. But eventually what happens? Once you've squeezed it enough, okay, no more, you end up with no more gas. Everything's either turn into either a solid or a liquid, and it becomes, so from point K onwards, okay, everything's turned into a solid. So the correct answer there is actually what? A or B. Okay, so B would also be a correct answer. All right. What would be the vapor pressure of your substance? At what point is the pressure here equal to the vapor pressure of the substance? That would be the pressure at points K or L, right? So this is the vapor pressure at this temperature. Okay, here's a plot of Z versus P for a substance undergoing liquefaction. Okay? Based on the dependence of the compression factor, we can say that this substance is below the critical temperature or above the critical temperature. This is Z versus P. This is an isotherm, so all of these data points are at the same temperature. Does this thing represent conditions below the critical temperature or above the critical temperature? Okay. Actually, I did say it was below the critical temperature, right? Below the critical temperature. Why? You can see that big dip right there. Okay, so that's another way of looking at this graph right here. Instead of pressure versus volume, you can plot Z versus pressure. Okay? And in fact, this pressure right here is the vapor pressure of the gas. Okay? So this is the vapor pressure. Up. So that's the pressure of the gas that would be in equilibrium with either the solid and the liquid that you can. See, a drop, remember what is Z? It's a ratio of volume to the ideal volume, right? So when you see that drastic drop in Z in your isotherm, that corresponds to liquefaction or deposition. Deposition is the opposite of sublimation, going directly from a gas to a solid.
Even if, say, that graph, they had to drop above where 1 is,
Uh-huh.
would still be considered below the critical temperature?
If you see that drastic dip, okay, then you are below the critical temperature. If you're above the critical temperature, you might see something that looks like this. There is no big dip. Okay, for example, over here, okay, you can, if you're above the critical temperature here, you might see something that looks like that. It's still going to be less than ideal. If this was the ideal, okay, it's still going to be, your real curve is going to be, it might dip below ideal and eventually it's going to overtake the ideal curve. But if you don't see that horizontal line, you know that you're not condensing, you're not liquefying, or you're not turning your gas into a solid. Okay, so that horizontal line in a PV diagram, in a PV isotherm, is indicative of liquefaction or deposition. Vertical line on the Z versus pressure indicates liquefaction or deposition.